Are we going? All right. So today we're going to talk about reconnection. Yeah, that's about it. I think I don't have anything folding over. Let's see, what did I do last time? I did waves last time and sunspots. And today I'm going to talk about reconnection. And reconnection is not on the homework, so it's very interesting and you should pay attention. But it's not on any of the homework problems. So there's that. So when you have two vector fields and you add them up and they're of opposite sign, what happens? If I have V1 equals 9x hat and V2 equals minus 9x hat, what is V1 plus V2?
0.
Is 0. All right. Magnetic fields do the same thing. You can do this with a magnetic field, but it's really hard. And the magnetic field hates it. But you can do it anyway, and the results are fascinating. So this process is called reconnection, where I have a magnetic field that is going in this direction, and I have another magnetic field that's going in the opposite direction. And so this is B, here's B. And here's a flow that's pushing these two oppositely directed magnetic fields close to each other. When they get close enough, so you keep pushing, then eventually they are occupying basically the same space, and the field strength here goes to 0. Now that's a problem because the field can't have an end. So if I'm going to eliminate the field here, then this one has to connect to something else. So this one has to connect to something else. So reconnection is really all about our favorite of Maxwell's equations. Div B equals 0. Which if that's not your favorite of Maxwell's equations, then maybe you have a different favorite Maxwell's equation. That one's my favorite, or least favorite, maybe both. But what this says is there's no free ends on the magnetic field. The magnetic field always touches back on another magnetic field. There's no endpoints. That's different from the electric field. Div E equals rho. So that means that if I take a little control volume, I can have a bunch of magnetic field coming out of it. My magnetic fields, or my electric fields, can stop on a charge, but my magnetic fields don't, which is a curious behavior, but that's the way it goes. So because they can't have any free ends, as soon as they touch here and the field gets eliminated, then this one connects to this one. And now I've got this ridiculous curvature, right? So here, now I have this incredibly large B dot grad B that I didn't have before, but now I have this huge curvature. And what's that going to do? That's going to start to accelerate the fluid. So B dot grad B is going in that direction. So this curvature here is going to accelerate the fluid in that direction and rip it off like shooting a rubber band. Does that make sense? So what we want to do is talk about this process. So this is postulated in the 50s by Sweet and Parker. Sweet didn't do a ton. Eugene Parker is one of the most important scientists of the 20th century. He's the only person that NASA has named a satellite after while he was still alive, which is a real ballsy move because satellites tend to blow up. So, naming something after somebody and then having it explode is not cool, but it didn't explode. So sweet. So they named the Parker probe after Gene Parker. He then passed away back in March of this year at the ripe old age of 94. But he was still giving talks. I saw him give a talk a few years ago, and he put up some of the slides that are in the book, like physical transparencies on an overhead projector, old school, like 1950s style talk. It was on transparencies. They rolled out a projector for him. It was awesome. And one of these, and he put up one of these slides that I didn't realize until a few years later when I started teaching the book. I'm like, oh, he's been using that same slide since, 1970 something. But here it is in the text. So he's a great physicist and did a lot of astrophysical magnetohydrodynamics. So we'll talk about Parker, I don't know, more. He's come up some, he'll come up some more. So the basic idea is, okay, let's just use dumb conservation laws and say, how can I smash a current sheet into another current sheet and get some reconnection. So I'm going to have an input velocity. That's my velocity of the flow pushing the two magnetic fields in opposite directions. I'm going to have an output velocity. This is how fast it shoots out the side. And I'm going to have a magnetic field strength. Sometimes my notes make better sense afterwards, and sometimes they make less sense. So we're going to invoke some of our favorite laws. The first being conservation of mass. The second one is energy balance. This velocity comes from this magnetic field that we destroyed. So the kinetic energy has got to roughly be equal to the magnetic energy out. And 3, we're going to assume we're in some kind of steady state, which is often a bad assumption, and here is a really bad assumption, but we're going to do it anyway because that's what was done before us. Okay, conservation of mass lets us say that VI times L equals VO times little l, where this is big L. This is the reconnection area, so this is the amount of magnetic field that you're destroying in the first place. And this, little l, is the width of the exhaust region. So you have some explosion and it comes out one way and it's getting rammed in the other way. So this is like stomping on a tube of toothpaste. You stomp on the toothpaste here, it comes out that way. It has some large area where you're stomping and some small area where it's squeezing out. So conservation of mass says VI times L is equal to V naught times little l. Does that make sense? Is that obvious why that's conservation of mass? Yeah, we're in 2 dimensions. This is only goes like length squared. We're assuming that nothing interesting is happening in the third direction. So conservation of mass gives us this. Energy balance gets us at 1/2 rho v squared. That's just the magnetic or the kinetic energy is equal to v squared over 8 pi, which is the magnetic energy. So, well, actually, let me take an aside here for a second. Let's talk about magnetic energy for a second. So I'm going to use B squared to be magnetic pressure in magnetic energy. So we can call this the magnetic pressure. because it behaves like a pressure. We can also call it the energy density. So I can refer to this as an energy or a pressure, because a pressure is really just a thermal energy density. There's a 3/2 somewhere in there kicking around if you want to be like really specific about it. But a pressure is just energy per volume, and energy density is just energy per volume. So 1/2 rho v squared is b squared over 8 pi. This is just saying that the kinetic energy that I have here came from the magnetic energy that I destroyed. And the last bit, steady state. In steady state, we have that del cross v cross b plus lambda del squared b equals 0. So this comes from the induction equation. So the induction equation is here. dB dt equals curl v cross b plus lambda del squared b, but I didn't put that up here. So this is just the curl v cross b plus lambda del squared b. So this is amplification versus diffusion. So I'm roughly going to be diffusing at about the rate that I'm cramming stuff together at. So actually calling this steady state is very silly, because these are not steady state processes. I'll show you a couple of movies. But it's not unreasonable to say that since we're looking at very small scale structures, the dissipation term is going to be important, and it's going to be roughly of the same order as the acceleration term, because what we're doing is smashing things together and seeing how small they'll get on their own. And that process is going to be set by the small scale physics, which is going to be set by the dissipation. So from this, okay, this turns into V times B divided by L. This is calculus equals algebra that physicists like to do. And this one is lambda B over L. So the 1 over L comes from the curl, and the V comes from the V, and the B comes from the V, and we ignore all of the vectoriness of this expression. So we need these two things to be roughly equal. Yeah, so then we do a little bit of algebra, and we're going to get an expression for what the input velocity can be to support this process. So this is really the rate at which I can be destroying magnetic energy. So from here, from 2, this gives us where'd it go? V output is roughly V alphane. You see why this says V output equals V alphane? This is output velocity. This is V squared, and on the other side is B squared over rho. There's a 2 that cancels that. So this, if we rearrange this, this is just saying that V equals B over the square root of 4 pi rho. That's just the alphane speed. So there's this really nice analog between the magnetic field strength and this thing called the alphane speed, that is the velocity of what things are doing, what the magnetic things are doing. It's the velocity associated with the magnetic field. So V naught is roughly VA. Let's see. The little length scale is going to be lambda divided by VI. We get that from here, from 3. So the length scale is just going to be the diffusivity divided by the rate that you're smashing things together at, the rate at which you are smashing things together. The rate you're smashing things together at. I like the second one better. So the length scale of this cushion is set by the diffusivity and how hard you're pushing on it. So that makes sense. So I've got some magnetic field. I'm going to shove it together, and the faster I can get rid of that stuff, the thinner the current sheet's going to be. So the diffusivity. Yeah, and then, so we do a little bit of algebra. We take this one, and we get that VI equals V naught little l over big L, which we plug in from here, and we're left with lambda VA over VI times L, which if you do a little bit of algebra says VI squared equals VA squared over the magnetic Reynolds number, square root of that guy. No, sorry. I have that squared, just the magnetic Reynolds number. So what this says, this is the Sweet-Parker reconnection rate, is that VI, this is the inflow velocity, is equal to the Alfvén speed, so this is how strong the field is, divided by the magnetic Reynolds number. That's how fast you're smashing things, or how thin you can make the current sheet. Now, the magnetic Reynolds number we can sort out is something like 10 to the 6 for the sun. So this is kind of problematic. So this is the Sweet-Parker reconnection rate. And that says that VI equals VA over RF. I'm actually going to write this. I'm going to clear some space so I have space for the other ones. So this is great, but it's way too slow. It's not the right model. This is not the way things work. But before we had really nice UV telescopes pointing at the sun all the time, this worked okay. But even then, as soon as they sorted this out, they said, well, okay, this is going to be something like a couple of centimeters a second, which is not what we see on the sun. And it's not going to generate enough energy to heat the solar corona, which is where we're going for this. So, okay, that doesn't quite work. And part of the problem is that this model is about a large, smooth sheet that's very nicely getting sandwiched into another nice, smooth sheet. That doesn't really work. So you can do some other geometry. So we're going to talk about Petschek and turbulent reconnection. This is the first one we're talking about, is Sweet-Parker. So Sweet-Parker is a great model. You can write it down really quick, but it doesn't really work. So Petschek said, well, okay, what if instead of one large thing that's trying to reconnect a buttload of field at once, we have things that connect like this. So you get these islands of magnetic field that will look like this. So we get these little current loops. So here I got a little loop of magnetic field now, which drives a little current. But that's okay, it does that. But you can reconnect at a bunch of points. So Petschek said, well, let's reconnect at a bunch of points and do a little math. And I've never actually sat down to go through this math, and I probably should. He has that, the inflow rate is equal to the Alfvén speed divided by the log of the magnetic Reynolds number. What's the magnetic Reynolds number again? Let's remind ourselves. The magnetic Reynolds number, just like the regular Reynolds number, is L times V over the diffusivity. So by connecting at a bunch of points, you can make the reconnection rate, instead of going like the square root of the log of the Reynolds number, goes like the log of the Reynolds number. So the square root of 1,000,000 is 1,000. The log of 1,000,000 is 6. So this is better. Here, I'll collect these things over here. And this was developed in the 60s or 70s. Sweet Parker was developed in the 50s, I think. Which is still a little slow and requires this specialized geometry and doesn't really come from anything natural. So the last kind of reconnection we'll talk about is called turbulent reconnection, and it's probably actually what's going on. And to say something meaningful about turbulent reconnection, I have to talk about MHD turbulence, which I'm not doing because I don't have the time. Because it's like, it really takes me like 2 days to go through MHD turbulence. And it's hairy and messy. But the upshot is, sorry. Compelled to talk about MHD turbulence very briefly. So this is the very short intro to MHD turbulence. So when we were talking about turbulence, we have this spectrum of energy versus wave number. Magnetic field, the energy goes like k to the minus 5/3. So this is a thing that we proved a couple of times, and you can see it in real life. Now, if I have a magnetic field, so the thing is, I have eddies. Maybe that's just a Y, A-D-D-Y. You have an eddy, and it shreds itself on about its turnover time scale. Now, when I get a magnetic field, the magnetic field doesn't want to bend because it's got a tension. So things are going to be kind of elongated along the magnetic field and not transverse to the magnetic field. So if I look at it in one direction, things get, as I get to smaller and smaller scales, the magnetic field becomes more and more important. Because if you look at the magnetic Reynolds number, LV over lambda, as L goes down relative to the lambda, the magnetic field starts to become more important. Because the magnetic field doesn't really get smaller as you get to smaller scales, but the scale gets smaller, but you still have this magnetic field. So at a smaller scale, B over L, the gradient term, is going to be bigger. So the curvature gets bigger when you get to smaller scales. So the magnetic field resists the bending as you get to smaller scales. And you get this complicated cascade that in one direction looks just like Kolmogorov. If you're looking at the velocities perpendicular to the magnetic field, they don't see this bending. So it behaves like Kolmogorov. But if you're looking along the magnetic field, you get a slightly different spectrum. So you have this process where the field starts to become more important at smaller scales. So when I have some kind of large scale business, I have turbulence. But when I get to smaller and smaller scales, So the turbulence has all of this small scale structure. We'll have some kind of local mean field, but on top of that is the turbulence. And now, instead of reconnecting on like 6 nice discrete islands or one large plane, now we reconnect on a fractal. So what's a fractal do? I haven't talked much about fractals, but fractals kind of fill space and don't at the same time, and that's one of the magical properties of a fractal, is that it's not a three-dimensional thing, but it can still be kind of everywhere. So the curvature becomes fractal, and the number of points where you can start to reconnect gets very, very, very large. Even though the points themselves become very small, they were small anyway. The point where a magnetic field can reconnect is basically infinitely small, because this is microphysics processes that's really going on. So in turbulent reconnection, the reconnection happens at a whole bunch of sites at the same time at a hierarchy of scales. So it's a fractal, which means that it's kind of space filling. But it's hierarchical. Meaning that there's some big things and some little things, and there's a spread in energy. Just like we have this spread in energy space, you have a spread in the number of sites where the thing can recombine. And our reconnection velocity becomes VA times the Mach number, the Alfvén Mach number squared. What's the Alfvén Mach number? The sonic Mach number is the velocity over the sound speed. The Alfvén Mach number is the velocity over the Alfvén's velocity. And it's really an important quantity when you're looking at dynamical systems. If you've got a dynamically turbulent cloud, times the min of the length scale at the let's call this little L over big L, 1/2. So we have a similar little L and a little big L, where the big L is the length of the structure and little L is the transverse width. So the geometry still matters somewhat, but it doesn't depend on the Mach or the magnetic Reynolds number anymore. It doesn't depend on the diffusivity anymore. The other two, Petschek and Sweet-Parker, both depend on the diffusivity, whereas turbulent reconnection doesn't. Let's get a better chalk. This chalk is breaking down. Let's upgrade purple. Nice long purple chalk. So here we've got VI equals VA times the Alfvén Mach number, all of these guys are squared, times the min sorry, new chalk is going to sweep of little L over big L to the 1/2 plus or minus. So the min just keeps this quantity less than 1. So what do we know? Here, let's actually so Sweet-Parker. I hate this chalk. Why is this so squeaky? Sweet-Parker is too slow. Petschek is faster, but still depends on the diffusivity. Turbulent reconnection is the fastest of these. This goes like VA times some large one number that's like 1 times something that's just going to be a geometrical factor. So the turbulent reconnection rate is by far the fastest of the 3 reconnection rates, and it's probably the one that is physically realized most often. And this one is responsible. The people responsible for this are Lazarian, who is another huge name in modern astrophysics. He's kind of an intense dude. And Vishniak. And they did this originally in 1999, but it's kind of ongoing work. So let's look at some reconnection. Here's all the sunspot videos. So we can see it happening. Every time there's one of these, like you can see these field lines showing up and breaking like all the time. It's really most apparent in this one. And you can see the little bright spots. So this is a couple of processes. You see these loops coming up like this because we had some loop come up to the surface and then bloop out. And then we've got some magnetic field line because it's buoyant because there's a magnetic field. The magnetic field provides pressure and drops the density, so it's buoyant, so it floats. And then it floats out of the sun. Then you have your left side and your right side, and you've got a loop like that. And then in that business, in the mixer, is reconnection. And one of the things that, and I have not gotten any, I need to, I need to get results from the Parker probe, because I'm sure that it's got cool movies. Oh, this is out of order. Here is, does this do something violent, or this is just the flow? You can see what's going on. We have a magnetic field that's kind of rotating. It's like a tornado, and it's dragging the field with it, but that's not the good one. I think did I number these? I didn't number these. Nope. I think these are the. So here is a DSO measurement from or SDO, the Solar Dynamics Observatory. And the best place to see it is in here. So this is where all the high energy photons are happening. But you have lower energy physics here. You have the corona. Here you have the surface of the sun. Here, the one in the bottom corner is a magnetogram. And it goes kind of fast, but you can watch it happen. Bloop. And there it explodes, and all the stuff falls down. And I think that this is over, let's see, the time is in the corner. This is over a span of an hour, I think. Let's see, I think this one is the same. Time scale, but it's slowed down a lot. So this is the same region that is doing its reconnecting. So the reconnection is happening down over there, and then this is the magnetic field line responding to that reconnection. And this is a different telescope looking at the same event. Oh. I think that actually this one, I didn't take good notes. This one is a different event, but this one is the same. Bloop. So you can watch the fields show up and bloop back down. So this is from the stereo telescope, which is pointing at the sun from the side. This is from the Solar Dynamics Observatory, which is looking face on. I guess they're both looking face on. It's round. Everywhere you're looking is face on. Let's see. There are other. So this is a pretty rare process. And, well, it's happening all the time, but it's really hard to catch on camera. Kind of like Bigfoot, except it actually exists. And this is a different event. Oh yeah, this is the one that I like best. Because here you can see the magnetic field is going in this direction initially, so you can see the stripes are that way. And then it rips apart, and now everything goes off in the transverse directions. So it all starts off like this, and then there's some violence, and then they go off to the side. And that's kind of cartoony. Version of this, or Sweet Parker is kind of a cartoon of this. Yeah, so let's see. Other things about reconnection. So, when have you actually seen the aurora? Like with the aurora borealis? I have not either. Someday I want to, but I've never lived far enough north for it to show up. But the aurora is also a process of a reconnection process. So this is a sketch of the magnetosheath of the Earth. So the Earth's at the center, and the sun is over in that direction. And the Earth has a magnetic field around it, and this magnetic field is really important because it keeps the solar wind from blowing the atmosphere of the planet off. So the atmosphere of the sun is all charged because it's 1 million degrees, so it's this stream of electrons and protons. That would all just rip the atmosphere off if it wasn't deflected by the magnetic field. So now you ask, how do particles from the sun get to the poles to light up the aurora? So the aurora, I should have some good aurora movies. That would be dope. Can I get one real fast? No, I got no internet. Nope, no internet. So the aurora is, green and blue, sometimes pink and red lights that you can see if you're at high or very low latitudes. And they're caused by charged electrons hitting the gas in the upper atmosphere. Where do those charged electrons come from? They come from the sun, but they don't come straight from the sun. They first take this 1,000,000-mile detour. So they come off the sun, and they get deflected by the magnetic field, which is what they're supposed to do. But the magnetic field isn't just a sheet, it's like a fishtail. So it comes back to the back and has a point where the field comes together. So what happens is electrons from the sun come along, get deflected away from the Earth, and then they wander back down these magnetic fields to this X point here, where the fields get close. And they are stuck here because it makes like a magnetic bottle. So remember, I drew one of these up a little bit ago, but I didn't talk too much about it. So you can make, if I have a pinched magnetic field condition like this, well, magnetic field gets real tight at the ends, then as a particle is spiraling along here, it sees the field get bigger and bigger and bigger until the field is very large, and then it will bounce off and go the other direction. You'll do that in E&M at some point. So you can make a magnetic bottle. And that's what's going on here. And then periodically that field will reconnect on itself and shoot the electrons back up the field lines, but now they're on a field line that closes on the Earth, or that connects to the Earth. Before, that's on a magnetic field line that isn't going to intersect with the Earth at all. So it's just, most of the electrons are just going to go right by, but they get piled up here and then eventually can reconnect, and that reconnection puts them onto magnetic field lines that can then hit the Earth. And that's where the aurora comes from. And there's satellites that they stuck back here. So this is what this graphic is about. This trio of satellites that they put back here, or they're in a very elongated orbit. I think this is the orbit. So they're on this very elongated orbit that takes them back through the magnetotail, and they can measure these reconnection events and these hot electrons. So that's pretty cool. All right. Let's see. What else do I want to say about reconnection? I think that's kind of it for now. So I'm going to spend the rest of the time talking briefly about the dynamo, and I'll do mean field dynamo Tuesday. Let's go back here. So the last question that I want to talk about is, where do magnetic fields come from in the first place? Why does the sun have a magnetic field? And it's not because there are giant currents. There are giant currents, but they're not what make the magnetic field. The magnetic field makes itself. So you'll notice that you really got to keep that diffusion term on. So this is the induction equation again, and it talks about the amplification of the magnetic field. So the sun has a magnetic field, and it's very strong. It's not very strong. It's like a Gauss at the surface. It's like thousands of Gauss in sunspots or in these coronas, but the mean field of the sun is about a Gauss. A fridge magnet is about a half a Gauss. The Earth's magnetic field is about a Gauss. The fields they make at the Mag Lab are about 1,000,000 Gauss, or 100,000 Gauss. The fields in magnetars are like 10 to the 15 Gauss. So how does this field come about? So what this term says, I can rewrite this term as just using one of my favorite vector identities. This becomes, okay, so there's a v dot grad b, a b dot grad v, a b div v, and a v div b. Let's see. This one is negative, this one is positive, this one is negative. This one is positive, but it's 0, so it goes away. I just happen to remember this vector identity, that curl of A cross B turns into this triple product of grads and stuff. And I like it because I like writing it in this way, because here, this v dot grad b, this is just the convective term. This is just the fluid moving the magnetic field around. So I'm sitting in a spot, I'm sitting on this tile in space, the velocity brings me some magnetic field, my magnetic field goes up. So somebody brought me some magnetic field, my magnetic field goes up. This term, b dot div v, this is just I've got some magnetic energy, and if I get smaller, the magnetic energy goes up. Just because I've got so many field lines, and if I squish them, there's more of them in a smaller region of space, so there's more magnetic energy. And this term, b dot grad v, well, we had another one, omega dot grad v, and I called this vortex tube stretching, because this is the gradient along the vortex tube of velocity. So this is the velocity at one side of my vortex tube versus my other side of my vortex tube. This one is the same kind of thing. This is the gradient of the magnetic field, of the velocity along the magnetic field. And as we said, things tend to move apart, so any material line tends to get stretched out. So this is stretching of the magnetic field. So this term is stretching. This one is advection. And this one is squishing. Now div v is usually close to 0. Div v is usually pretty small. Things are usually pretty incompressible unless you're smashing on things. Unless you have an explosion, div v is usually pretty close to 0. So we can usually ignore the squishing term. And we're just left with advection, which is just pushing stuff around. and the stretching, which is a lot harder to get your head around mathematically. So the induction equation supports stretching. So how do you stretch out a field? So the sun, let's talk about the sun's dynamo for a second. The sun is differentially rotating. That means that it's rotating at the equator faster than it is at the poles. So that means if I have a poloidal magnetic field, a poloidal magnetic field is one that goes along the meridian. It's pole directed. It's going to get stretched out because this part is going to be, so the magnetic field line is along here. Velocity is higher here than it is here, so that's going to be stretching, right? I have a velocity gradient along my field line. It's going to get stretched. So this will get pulled out and amplified along the direction of rotation. So the amplification happens when I have some poloidal magnetic field that gets stretched. So how do I get toroidal? How do I get poloidal magnetic field? I don't always start with that. If my field is in this direction, this is a toroidal field, like a torus. This doesn't get stretched out because the differential rotation is in that direction. So this kind of field isn't going to get stretched out. But I can turn a toroidal field into a poloidal field with convection, because this again is differentially rotating. So if I have a blob that rises, what's it going to do? It's going to spin up. So if I have a blob that starts to go up a little bit because of the Coriolis force, it will rotate. So Coriolis turns so the Coriolis force takes toroidal magnetic fields and blooms them up and then turns them into something that looks like this. And then I have some poloidal field. And poloidal field plus differential rotation gives you amplification. And then that process continues and rotates the poloidal field back into toroidal field, and eventually you get more magnetic field from this process. So this is kind of like have you guys ever watched a taffy puller at the state fair? Those big machines that just go, they just stretch on the glutens in the candy to make really strong candy. This is the same kind of process. You've got this mixer that's going in a bunch of different directions. So the important bit is that this is a fully three-dimensional process. I start off with one direction of field. The three-dimensional processes turns that into the other direction of field, which then can get stretched out by a differential rotation, which can then get rotated back into the toroidal field of the sun. So by this process, and the process is often referred to as stretch, twist, and fold, which is also the name of a book. By this process of stretching, twisting, and folding the magnetic field back on itself, we get more magnetic field. So this is the Parker dynamo in a very tight nutshell. It's the relationship, this dance between toroidal magnetic fields, Coriolis forces, poloidal field, and differential rotation. Now, all of these things, this is kind of horrible, but they're all necessary. I'm going to show you. Should I do it now? Yeah, I'll do it now. It turns out if it's not fully three-dimensional, then it doesn't work. So I'm going to show you a cartoon of what something that doesn't work. And this is important. This is called Cowling's anti-dynamo theorem. And what it's, so now there are many. And if you really go down this rabbit hole, there are several anti-dynamo theorems that you should be familiar with. But we'll just talk about the first Cowling's one. What he says is that there is no dynamo that is so there's no dynamo that has both an axially symmetric velocity and magnetic field and is in steady state. The sun is in steady state. It's got this 11-year cycle. It's really a 22-year cycle of the magnetic field grows. Oh, I should have put up the butterfly diagram of the sunspots. I forgot to do that. It grows and then decays on this 22-year cycle where it gets really large, and then there's a buttload of sunspots and a bunch of magnetic activity, and then gets smaller, and then the field flips over and it does it again. So the sun is basically in steady state, and it's basically axially symmetric. That is a pretty round object. But the dynamo that makes it is not axially symmetric. It's not steady state. So this is what Cowling's anti-dynamo theorem says. Well, I'm going to show you this theorem now. And it's relatively painless. So if I've got some round object and I've got some magnetic field that's wrapping through my structure, and I just take a plane and I cut through my structure, my object. Here's my axis of rotation. I'm going to have magnetic structures that look basically like this. Now there might be some magnetic field coming out of the plane as well, but in the plane the magnetic field looks like this, and there will be some fixed point where the field is 0 in this plane. This is by this assumption of axial symmetry. And because of axial symmetry, my field is going to basically look like this. Maybe it does something a little bit more complicated, but it's going to be symmetric, and there's going to be a point in the center of my magnetic business where the field is small and driven by a current. So along the annulus that's in this along my stagnation point, I'm going to have some current. We'll call it J phi. And J phi by Ohm's law is sigma times E plus V cross B over C. So if I integrate this along this circle, the integral of J along C, let's call this curve C, the integral of J along C, that's not going to be 0 because J is going to be basically constant in one direction. So this is going to be something that's large and not zero. So that's the current that's driving this magnetic field. Look on the right-hand side. V cross B. So let's integrate along this curve. We'll have a term that looks like the integral of V cross B dot dl. And here, we only have a B phi because of the construction. We have this stagnation point. We'll only have field into the page. So BR and BZ will be theta are both 0. And B is then going to be along DL. V cross B is going to be perpendicular to B, and so it's going to be perpendicular to BL, so this is going to be 0. So this term goes away because it's got to. So I'm left with the integral of the current is just the integral of E dot dl along this curve. So E dot dl is equal to the integral of along the area of curl E dot dA. This is Stokes. This is just another application of fundamental theorem of calculus. This one is the Stokes version where you've got a loop, turns into a curl. And we know from Maxwell that the curl of E is equal to the integral of -1 over C dB dt, which is 0 because we assumed that we were in steady state. So I got a thing that's not 0 is equal to a thing that is 0, so that says one of these assumptions has got to be violated. So either my axial symmetry has to be violated or my steady stateness has to be violated. So I can't have always increasing magnetic field. It's got to do something cyclic. It's got to do something complicated. So that's why Parker's dynamo has this complex three-dimensional behavior to it, because it's got to break the symmetry. The symmetry of the problem kills the dynamo if there's too much symmetry. Let's see. I'm not going to get into mean field theory today because it's kind of long. Yeah, does anybody have any questions about any of these things? Is there anything I'm going to wrap up there? Everybody good? So we talked about the important takeaway. Oh, did I erase it? Man. The important takeaway was right here. So there's 3 different models of reconnection. And the book talks about 2 of them, but the third one, which is probably the one that's right, wasn't invented until after the book was written. So it's such a problem of using an old book. It's a good book, though, so, you know, a book doesn't exist that has everything that came out last week and also a great description of everything that was done 200 years ago. So anyway, 3 kinds of reconnection, and Parker's dynamo, and Cowling's no dynamo theorem. Those are the takeaways for today. And that's all I got. Let me know if you have any questions, and have a good turkey.